So these are essentially the definition for relative velocity is an observation made with different reference frames, right? Or a different point of view, right? A frame of reference is like a point of view. And we're going to talk about their relationships with each other. So this section deals a lot or has a lot of examples of things like wind currents pushing objects, water currents pushing objects, things like that, where it might look like we're going one way, but the water current is pushing us, another way, or the wind is pushing us another way. So that's a lot of what this section of the chapter is about, is how it might appear to us standing on the ground, where it might be really going a different velocity up in the air, things like that. Okay, so you don't have to write down this example, but I want you to think about it. Okay, so if I have two trains traveling the same speed, right, in this example, 80 kilometers per hour toward each other, okay? If they're traveling in the same direction, and I'm standing on the side of the tracks, right, I can view both of those, and I'm standing still, right? So we could view, or we could see, that both of those trains are traveling at approximately equal speeds, right? Would you agree with that? If you're standing to the side, you could be able to tell that those two objects are pretty much moving the same speed. Agreed? When things change is when we become part of one of the objects, right? If I'm standing now on one of the trains, so someone standing on the train, which changes your frame of reference, we'll look at this oncoming train as going twice as fast, right? You are traveling 80 kilometers this direction. The other train is traveling 80 kilometers per hour this direction. You are closing that distance between you twice as fast, right? So it's going to appear that thing is coming at you 2 times as fast. Does that kind of make sense? Can you envision what I'm talking about there? Right? When you change your frame of reference, it changes the way you see things. Those things, both of those examples were called same line velocity, which means we just did simple addition or subtraction to figure out how fast we thought those objects were going, right? If they were going, they're coming towards each other, we added them together. If they're going in the same direction, right, we subtracted them. You guys did the math pretty quickly and pretty common sense. So that's not something that we need to focus on a whole lot. But same line velocity just means like, if they're moving in the same direction, right, that's going to seem like they're going maybe not quite as fast, but if they're coming towards each other, maybe like they're going twice as fast, or a combination or addition of those two things. Okay, so let's see, let's look at this example. He starts out by skating 3 meters per second west. If I push him and he ends up traveling 5.3 meters per second west, what was the speed of my push, right? What speed did I give him to end up that way? So here's his initial velocity, right? 3.0, oops, he's west, sorry, not east. We have to go back to drawing our vectors here. So that's his vector. His resultant vector is this one. He ends up 5.3. So my push had to have been in what direction? The west, right? If I would have pushed him east, it would have made him look like he was going slower than he actually was, right? So my push has to be that difference between those two. Does that kind of make sense? So that means the speed of my push was 2.3 meters per second west. 2.3? 5.3 minus 3? Okay, if he was going west, let's say this. If he was going west and I ended up pushing him east, right, it's going to slow him way down so that maybe it looks like he's only going, 0.7 meters per second west. Like let's say all the values were the same and he was going 3 meters per second and I pushed him backwards, right? He's going to still move forward, but he's going to slow way down, right? Because I pushed him in the opposite direction. Does that kind of make sense? Okay. It's kind of one of those things where, at the airport, you step on those things that make you walk fast. You know what I'm talking about? Those flat things. And, and you can walk the other direction. Like you're really walking, but it doesn't look like you're going anywhere. That's what's happening. Or you can walk and it looks like you're going really fast, right? That's the same relative velocity. Okay. Now, that's same line velocity. It's really simple. We won't see too many of those problems, but maybe a couple. Now we're going to move on to if they're not in the same line, which means they're not directly in line with one another, right? They're at an angle now. Now we have to use vector addition to help us find the velocity of those objects. Okay, and vector addition is when we draw our right triangles. Okay, we break down our vectors into x and y, add all of our x's, add all of our y's, build our new triangle, right? That's vector addition. So we're going to go back to that here a little bit. Most of the time, relative velocity is a pure right triangle, so it's a little bit easier. Okay? This is really important. In relative velocity, it's extremely important to draw a diagram because the questions for relative velocity are worded kind of confusing. Okay, it really takes a little bit of breaking it down into the word problem to figure out what's really going on in the situation. Okay, so when you're drawing your diagram for relative velocity, you need to be really careful and really thorough. And we need to make sure that we think about the fact that our resultant vector should always be our overall final velocity. Okay, so that doesn't mean that we're always going to solve for the resultant or solve for the hypotenuse. But the resultant always needs to be the final, what we're looking at velocity. Okay, and I'll explain that a little bit more here in a second. Okay, so the resultant is not always your hypotenuse. Okay, I'll put that in here. It's not always the hypotenuse. Okay, and I'll show you an example of that here in a little bit. Okay? So relative velocity questions are going to take you being able to step back and really think about what's going on in the problem. Is he swimming this direction and the current's pushing him here? Or what's his overall goal? Things like that. Try this example, and I'm going to walk you through it. I'm going to show you how we draw our diagram, all that kind of stuff, okay? So you have to read these questions carefully, okay? He is attempting to get straight across the river. His goal is to end up straight across from where he started. Okay, that's his goal. So he has to take into account where the current is pushing him. Would you agree? His goal is to get straight across the river. Okay? The river's flowing 1.2 meters per second to the west. Okay? He needs to be traveling 1.8 meters per second on its path. What speed and at what angle should he leave the shore? Okay, so that's what it's asking. So when we draw our diagram, we have to be really, really careful here. Okay, so let's read through it one more time. His goal, right, here's our coordinate system, right, here's my boat. His goal is to end up across the river right here. Would you agree with that? That's his goal. So he wants to end up here. This is our resultant vector, right, because that's his overall goal. Okay, to get there, if the current is pushing him to the west, which way does he need to leave the shore? Just give a general direction. Right? It needs to leave to the east somewhere. Okay, I'll draw that in a different color. Okay, if the current is pushing him to the west, he needs to leave this direction. Right? He wants to end up straight across from where he started. The current's going to push him to the west, so he needs to leave this direction to have that current push him back to where he wants to be. Okay, are we on the same page with that diagram? Yes or not so much? This orange is our resultant vector. So we had to add them tail to tip to get to that resultant vector. Okay, this orange one was the overall goal here. Okay, I'll rewrite result.
It's asking for the speed.
It's asking for this blue line. How fast did he really need to go? Right? If he wants to be traveling 1.85 and the river is pushing him 1.2, so how fast does he really need to go if he wants to end up moving 1.85 meters per second straight across? So we want to find
3.05.
whatever the hypotenuse of that triangle is. I haven't plugged it in yet. Right? He's working with or against the current here. What do you think? Is he working with the current or against the current? Against, right? The current's going west. He's leaving to the east direction, right? Because he wants the current to push him back straight across. So he's working against the current. He's going to have to go faster than 1.85.
But he's like using it.
Yeah, but if he would just left the shore and just started swimming, the current would push him this way, right? He's working against the current to get him back to where he started.
So then the only way to work with the current is just going straight towards it.
Yeah, the only way, it would say like he just leaves straight and he's going to end up down shore somewhere, right? He would let the current push him.
Oh.
So find the hypotenuse of that triangle. It should be greater than 1.85, right? We can't have a hypotenuse less than one of our sides. 2.21, is that what you said? Okay. Okay, so 2.2 meters per second at, we got to find that angle as well. So how do we find the angle of that triangle? You could do second of anything. I'm probably going to use the numbers they gave us, so I'd use second tangent, but that's up to you. Because if your hypotenuse is wrong, then it means your angle would be wrong too, but you can use anything.
Why do we have to find the hypotenuse?
The hypotenuse tells us the speed he has to leave at. The angle would tell us at what angle he's got to leave the shore at. So he's saying he's got to leave in exactly this direction at exactly this speed if he wants to get straight across from where he started. So I would use second tangent to solve for that angle, and I got about 33 degrees. I did second tangent of opposite over adjacent. So 1.2 divided by 1.85. Yeah, make sure your calculator's in degrees, not radians.
What does it mean?
Okay, this says the same boat. All right, we're starting our situation over again. Doesn't really matter if it's the same boat or a different boat. Leaves the shore, driving straight across. So he just leaves driving straight. He has a velocity of 1.9. The current is pushing him west at 1.45. So if I was standing on the shoreline, what would I see his actual velocity being? Right? So let's think about that. If he leaves straight and he lets the current push him to the west, right? If we stood on the shore, it would look like he's going at this angle. Right? Would you agree with that? Okay, so when we start to draw our diagram, we say, right, he leaves straight across. The current pushes him to the west. So if I was standing on the side, it would look like he was traveling in this direction. Right? So this is our resultant vector. We're going to find that angle and that hypotenuse. So he leaves. He knows he's going 1.9. We don't know that on the sideline, but he knows that, right? The current's pushing him 1.45. We want to find out if we stood on the shore, it's going to look like he's moving faster than he actually is because the current is working with him, right? The current's pushing him west because he's letting it. Okay, so let's solve for that hypotenuse.
Is this stuff going to be on our quiz?
What do we have for our hypotenuse here and our angle? Okay. 2.4 meters per second at what degrees? 37 degrees what of what? Good, west of north. Perfect. Okay. So as long as you draw your diagram that straight across is north, right, your angle should always be the right direction. Okay. Any questions over these couple? Okay. Okay, these two are riding on a ferry that's traveling east, traveling purely east at a speed of 4 meters per second. They roll a marble with a velocity of 0.75 meters per second north. What is the velocity of the marble? Okay, so if I was looking at it from a different angle, right, if I took myself out of that frame of reference and I just watched the marble itself, where would it look like it's going? Okay. No, this will have the hypotenuse being the resultant vector. So the ones where it's not would be like if his goal is to end up straight across from where he started. Okay, that would be our resultant, and we'd add things tail to tip to get there. Okay. So here we say the boat is moving east, right? The marble rolls 0.75. This was 4. So if I was just looking overhead at this thing, it would look to me as though it's traveling at this angle, right? It'd be hard to tell, but that's what it would look like to us. So that's mostly what relative velocity is using right triangles. But the drawing of the diagram is the most difficult part. Okay, making sure things are in the right place.
So why is the 0.75 the opposite or whatever?
Because it's going north.
She
So the boat itself is going east. The marble's going north.
did she drop it at the beginning?
Well, I mean, yeah. The boat's going this way. The marble's going this way. Right? So if I was looking at it overhead, it would look to me like that marble's going at an angle.
The boat's going east. Wouldn't the marble look like it's going west?
Not if she rolled it to the north.
How's she rolling? How's she rolling?
4.1 meters per second at 10.6 degrees.
Smart guy, huh?
Most of the time?
Most of the time, our resultant is our hypotenuse. But like Lauren was asking, if we have the times where it's not our hypotenuse means like if our goal is to end up straight across from where we started, that's when our resultant is not our hypotenuse. You want to try this one on your own? Okay, go ahead and try this one on your own. I want to see the diagram before you start doing any math. Okay? So as I walk around, I want to see your diagram for this problem before you can move on. Diagrams. We know we're flying 200 kilometers per hour north. If I stand on the, and I know that the current is pushing me to the east, right? So if I stand on the ground, it looks to me like they're flying 243.2. At 34.67 degrees. So I need to find the speed of the wind current. A lot of you tried to draw your diagram like this. 200, this something, 243. Right? That does not work. Right? This does not add tail to tip to get to our resultant vector. Where's our 34 degree angle go? Right? That angle always has to touch the origin. So right now, if it touched the origin, that's a 90 degree angle. Right? That doesn't work. So we have to make sure that our vector always forms a right angle, not at the origin. Right? So 243, this, and 200. Okay? That angle has to be touching the origin. Okay, so to solve for the wind current, what did you, which trig function did you use? Didn't really matter, I guess.
Pythagorean theorem.
Yeah, Pythagorean theorem, that works. Okay, or you could have used really any of your sine or cosines. Okay, what did we get for our wind?
138.
I don't know. Maybe that's wrong. 138.4.
Okay, so what would our units be? Kilometers per hour or what?
Per hour.
Yeah, but what direction?
Oh.
East.
Purely east. Okay, does that make sense? So you have to read the problem to figure out what's our overall goal here. Right? If it says he's going to end up straight across the river, that's got to be our resultant. We have to add things tail to tip to get to that resultant.